This fairly simple expression has two variables and one OR operation and one AND operation, but there's scope to simplify it. This is the combination of logic gates that it represents. First, let's add some brackets for clarity. Strictly speaking, these brackets aren't necessary because the AND operation has a higher precedence than the OR anyway. At this stage you might have spotted that we can use the absorptive law and simplify this expression in just one step. But suppose for a moment that we don't know about the absorptive law. There are some useful transformations to learn about here. We'll begin by converting this single A into A and 1 using the identity law. At first sight, a backward step, the expression is bigger than it was. But keep watching, this counterintuitive move has a purpose. We can now apply the OR distributive law to factorise this expression. Here it is with one of the A's factored out. This has revealed an opportunity to use the annulment law, which states that a variable ORed with a 1 is a 1. Here the variable b is being ORed with a 1, so it becomes simply 1. Finally, we can apply the identity law. Any variable ANDed with a 1 results in itself. We're left with z equals a. So these two expressions are equivalent. The output of the circuit is always the same as the input. The circuit is redundant. In fact, what we've just done is prove part of the absorptive law, the Or absorptive law. That is, A, or A and B, equals A. Let's see another example. Again, let's pretend we haven't spotted that we can use the absorptive law yet. Note that the brackets are essential this time. They specify that the OR operation should occur before the AND. We'll expand the brackets according to the distributive law. Then A and A can be reduced to just A according to the idempotent law. What we have now is exactly the same as the previous example. We could simply say, let's now reduce it to A using the half of the absorptive law that we've already proved. Or we can work through exactly the same steps again, and ultimately we'll arrive at nothing more than A. We've just proved the second part of the absorptive law, the AND absorptive law. A and A or B equals A. Let's look at an example that makes use of the absorptive law. Perhaps you'd like to try it for yourself before I show you a solution. There's a multitude of ways that you can approach this problem, and they're all fine if they arrive at the same result. You shouldn't be afraid to try something out and backtrack if it leads to a dead end. Pause the video now if you'd like to give it a go, and I'll show you one possible solution in a moment. Let's run through a solution then. Straight away we can see an opportunity to apply the AND absorptive law. Now it's tempting to remove one of the b's sitting outside of the brackets because b or b is b, but be careful. These extra brackets make it clear why this would be wrong. The leftmost b is being ANDed with an a, and this operation has a higher precedence than ORing the b with anything else. However, these brackets have revealed an opportunity to apply the OR absorptive law. A and B, or A, is essentially the same as A or A and B. Remember the commutative law? So this term can be reduced simply to A. With no other obvious reductions to be made yet, I'm now going to expand these brackets according to the AND distributive law. With a little rearrangement, as permitted by the commutative law, we've revealed an opportunity to absorb again. And so we have our final simplified expression. These two very different combinations of logic gates will do exactly the same job. Here's a few different expressions you can attempt to simplify yourself. Pause the video now if you want to give them a try. Take your time, and I'll run through some solutions when you resume playing. Here's solution 1. I'm going to use the distributive law to expand the whole term. I can now use the idempotent law to reduce A or A down to A. I can use the absorptive law to turn this term into simply A. And I can use the absorptive law again. With 3 variables, this is probably as simple as it gets. Here's solution 2. First thing I'm going to do is expand this part of the expression using the distributive law. Now I'm going to use the complement law to reduce not C or C down to 1. The idempotent law allows me to reduce B or B down to B. There's an opportunity to absorb here. There's another opportunity to absorb. And yet another opportunity to use the absorptive law. Finally, B and 1 becomes B according to the identity law. Solution 3. This one's tricky, but definitely worthy of study. I'm going to add some brackets for clarity. Notice how the or operation is now more prominent, but the terms that were being anded together are still being anded together. I haven't changed the meaning of this expression. I'm going to use the distributive law to factorise it. I've pulled A out of each set of brackets. My next move is to use the identity law to change not C into not C and 1. This might seem like a pointless move, but look at what I do next. I'm going to factorise again, but this time I'm pulling not C out of the expression. By doing so, I've revealed an opportunity to use the annulment law. B or 1 becomes 1, and this has revealed an opportunity to use the identity law. Not C and 1 becomes not C. There's my final expression. To summarise, simplifying a complex Boolean expression minimises the number of logical operations and variables involved. This makes it a powerful technique for simplifying complex logic circuits. The laws of Boolean algebra represent patterns of variables and operations that can be manipulated, reduced, and ultimately eliminated from a complex expression. Mastering these laws takes care and plenty of practice. Occasionally you'll run into a dead end, so you'll need to backtrack and try another approach. Knowing you've succeeded in simplifying an expression as far as it will go is one of the challenges you face when learning this skill. Unlike a game of chess, you don't always know when you've won. An online Boolean algebra calculator can help you with this. It will let you see the minimised form of a complex expression, and it will let you check that your intermediate forms are on the right track.